Okay, in this video we're going to look at 4 basic proof techniques used in mathematics. And what we're going to do is talk about direct proof, proof by contradiction, proof by induction, and proof by contrapositive. And again, this is just going to be a quick little introduction. We're going to do, the result that we're proving is going to be something very basic. You might even think, do we really need to prove that? But again, what we're trying to do is focus on these techniques and how they're used. In some other videos, I'll do some more direct proof, proof by contradiction, induction, and contrapositive examples. And we'll do some that are more complicated. So again, just trying to focus on the techniques here. So if you're new, again, to writing proofs, hopefully this will steer you in the right direction. So we're going to prove one of these if-then statements, if P then Q, and we're going to use the 4 approaches we just mentioned, those different types of proof techniques. So what we're going to prove in each case is we're going to prove the following. It says the sum of any 2 consecutive numbers is odd. And again, not a mind-blowing result by any stretch. So, right, 3 plus 4 is odd, 4 plus 5 is odd, 5 plus 6 is odd, etc., etc., etc. And to do that, well, we're going to use some definitions. So, definition 1. So, an integer number n is even if and only if there exists an integer k, so that we can write that number as n equals 2 times k. Definition 2, so an integer number n is going to be odd if and only if there exists an integer k such that we can write n as equal to 2k plus 1. That's going to be the definition of an odd number. And definition 3, 2 integers a and b are going to be consecutive if and only if b equals a plus 1. So one of the numbers is one larger than the other one. All right, that's what they're saying. Okay. So this statement, the sum of any 2 consecutive numbers is odd, it may not at first glance feel like one of these if P then Q statements, but of course you could rephrase this slightly, and we could put the if then in there and say, well, if A and B are consecutive numbers, then the sum of A and B is odd. So that's going to be our if then statement, just to make it really crystal clear here. So, okay, so let's actually start doing these. We'll take a few minutes to get through all 4. Shouldn't take too terribly long, though. So let's look at the direct proof first. So let me zoom out here a little bit to get everything in there. Let's zoom out a little bit. Okay, so direct proof. So this is going to be our first proof technique. So the basic idea of a direct proof of if P then Q is we're going to assume that the statement P is true. So we're not even going to, work on justifying that. We're going to assume that we have some statement that's true, and we're going to use that true statement P to show that Q is true. And this is, typically in a proof, that's going to be the hard part. So that's the part that's going to require a little bit of legwork. So one little remark here, I say learn to read, reread, understand, and love your definitions. A lot of, especially very fundamental things that you prove at the very beginning, you're going to try to show that some form or some definition is being satisfied. So in my case, we're going to show that, this n equals 2k plus 1. We're going to keep referring back to this form where k is an integer over and over. All right, so let's prove this if a and b are consecutive, then a plus b is odd. So let's assume this is going to be our proof now. And I'm going to be a little sloppy here, my handwriting. So we're going to assume that a and b are consecutive. So we're assuming that those are consecutive integers. Well, that means we know that we can write b as a plus 1. We can write one of the numbers as the other number plus 1. That's what we're given because, again, that's what it means for them to be consecutive. So here's our argument. Here's the big justification. Well, we could write a plus b. That's what we're trying to show is odd. We could write a plus b simply as, well, we could write it as a plus, and we said that b is equal to a plus 1. So I'm just inserting that there. So we're writing a plus b is a plus 1. Well, I can simplify this and say that that is equal to 2a plus 1. And this was the definition of a number being odd. So a plus b equals 2a plus 1. We said we had to have this form of 2k plus 1, where k is an integer. And again, I'm going to, we're assuming, again, that A and B are integers. They're consecutive integers. I said I'm going to be a little sloppy and not write everything out. So we're now done. Proof complete. So we've written the sum A plus B in this form 2A plus 1, where A is an integer. And we said that's the definition of a number to be odd, is if we can write it as 2 times some integer plus 1, that means that value's odd. So boom, we're done. Proof complete. Sometimes you'll see little boxes at the end of your proof. I used to always like writing those because it made me feel like I had done some major accomplishment here. So let's see. So that one, again, simple result, so we're not going to have to do a ton of work in this case. Let's look next at proof by contradiction. So just a brief outline of what's going on here. So the idea is, right, that a proposition is either true or false, but not both. So we get a contradiction when we can show a statement is both true and false, showing our initial assumptions are inconsistent. If we get a statement that's both, if we've got something that's true and false, something's wrong somewhere, right? So we use this to show that if P then Q is true by assuming both P and not Q are simultaneously true, and then we derive a contradiction. So when we reach this contradiction, it means that one of our assumptions cannot be correct. Either our assumption about P is not correct or not Q is not correct. And typically we'll assume that P is true. We'll just oftentimes assume that it is true. So that by default, the inconsistency must be that not Q is false. And if not Q is false, that means that Q is true. And that's what we want to do. Okay, so let's look at our example here. Let's prove again that if A and B are consecutive integers, then the sum A plus B is odd. So again, we're going to assume, so here's our if part, we're going to assume that A and B are consecutive integers. So I'll put integers in here. I feel bad that I didn't write it in the last one. So let's assume that A and B are consecutive integers. And now let's assume, though, that sum A plus B is not odd. So let's assume that it's not odd. Okay, well, if it's not odd, and again, when I say if it's not odd, the sum, if A plus B is not odd, then what happens? Well, there's no integer k. There's no integer k such that we can write the sum A plus B equals 2k plus 1. If this sum A plus B is not odd, again, we said if k is an integer, 2k plus 1 is going to be odd, so there's no k so that this happens. This does not hold true. But we've already seen, as in the previous example, that we can write the sum A plus B, we can write that as A plus 1, because A and B are consecutive. Well, that gives us 2A plus 1. So we've got a contradiction here right now. We've shown that A plus B does not equal 2k plus 1, where k is some integer. But we also have shown that A plus B does equal 2a plus 1. And again, A is an integer. So this is our contradiction. These two results, these contradict each other. So we're assuming that A and B are consecutive. So it must be incorrect that our second assumption, that A plus B is not odd, that's not correct at all. That's our inconsistency here. So by default, it must mean that in fact A plus B, the sum A plus B is odd. And that would be again our proof by contradiction. Okay, so we assume that they're not odd, the sum is not odd, so we can't find this integer k so that A plus B equals 2k plus 1. But hey, we certainly can, because A plus B, we can write that as 2a plus 1. It says we can never do this where k is an integer, but we know that A is an integer. So that's going to be our contradiction, and we've got this result that A plus B must be odd. Some people don't like proof by contradiction because a lot of times a direct proof, for some mathematicians, a direct proof is nicer. because usually there's more information that's given. You do something a little more constructive. And a lot of times with a proof by contradiction, you're just showing that a result doesn't hold, but oftentimes, well, sometimes it doesn't give you any insight as to why something is true. So some people don't like proof by contradiction. I was always a big fan of it. I seem to have good results with it. All right, proof by induction. So you may have seen proof by induction again in a pre-calculus class, a calculus class. I've definitely seen people, run into these in high school, and they're certainly not taking some advanced math course. So proof by induction. So proof by induction is a method to show an infinite number of facts by showing some specific case holds, and then using the assumption that the proposition is true for some value of n. We assume that the proposition is also true for n plus 1. So the idea is, when you're showing that it's true for some value of n and that it's also true for n plus 1, you're kind of showing that, well, if it holds for one case, it holds for the next one. But then again, because of that generality, it would hold for the case after that as well, and the one after that, and the one after that, and the one after that, etc. This first part, showing that it holds for a specific case, kind of gets the whole ball rolling. It's kind of like if you have a bunch of dominoes. It's kind of, dominoes, right? So if one knocks over, the other will knock over. And if that one knocks over, the other one will knock over. And if that one knocks over, the other one will knock over. Well, okay, that means that they'll all knock over as long as we can get it started. And that's what this specific case does. It kind of gets it started, and then this general result shows that it will keep going on and on indefinitely. So, okay, so let's repeat this. We're going to show that a propositional form P of x is true for some basis case. So this is just kind of terminology gobbledygook. We're going to, assuming that P of n is true for some n, we're going to show that this implies that P of n plus 1 is true. So again, we're showing it holds for some n, then it holds for n plus 1 as well. And then again, just by what we said by the principle of induction, it's going to follow that this propositional form is true for all n greater than or equal to the basis case. Okay. So let's write our proof out here for induction. Okay, so we're going to let, we'll let the propositional form f of x be true when the sum of x and the number following it, its successor, is odd. Okay, that's when our propositional form is going to be true. So let's consider our base case here. So our basis, either our base case or our basis. So we'll call this the base case here. Let's consider the propositional form f of 1. Well, f of 1 is going to be, so notice the sum 1 plus 2 equals 3 is odd, because we can show there exists some k that belongs to the integers. So from the previous video, remember this little backwards e remembers there exists some k belonging to the set of integers. Maybe you remember from hopefully your math classes, the set of integers. We can write that as a capital Z. So we can show that there exists some integer such that, you can read the colon as the word such that 2k plus 1 equals 3. Because again, that's what it means to be odd, right? We have to be able to show that there's some integer k so that 2k plus 1 equals whatever number we're claiming to be odd. And namely, that's when k equals 1. When k equals 1, we'll have 2 times 1 plus 1. Well, that's 3. So that certainly satisfies that definition of being odd. So we've now shown the base case. Okay. So now our step 2. So we're going to assume that. So now let's assume that f of x is true for some value of x. Okay, so this is now we're going into the realm of generality. Well, if it's true for some x, well, we know that x plus its successor, which would be x plus 1, we know that that's odd because we're assuming that to be true. So x plus its successor is odd. Okay, so next what we're going to do, notice that if we add 1 to x and then also to x plus 1, so I'm going to add 1. So notice if we add, so I'm going to take x plus 1 plus x plus 1, and we're going to add an extra 1 in there as well. Well, what's that going to give us? That's going to give us x plus 1 plus x plus 2. Notice I'm not simplifying it all the way down. And this would be our statement f of x plus 1. This would be our propositional statement f of x plus 1, because we said our propositional statement, we take whatever number that's next to our f, that's inside of our f, and we take its successor and we add those together. So this is going to be the propositional statement f of x plus 1, and we can certainly claim, so our claim here is that since x plus 1 is odd, what did we do? Well, we really just added 2, right? We added 2, we added 1 plus 1. So since x plus 1 is odd, adding 2 to this value, again, gives an odd number. This again gives an odd number, and that would be proof complete. So since x plus 1 is odd, well, if we add 2 to that, it's still going to be odd. But when we write x plus 1 plus x plus 2, that's going to be our next propositional statement. So assuming that f of x is true, we've now justified, and true in the sense that it's going to be, this statement is odd, we've now shown that its successor is also odd. Okay, so that would be a proof by induction. So that would be our general step here. Last but not least, let's look at proof by contrapositive. Okay, so proof by contrapositive. So the contrapositive of the implication if P then Q, the contrapositive of that is if not Q, then not P. And these propositions are equivalent. And what that means is that if you can prove the implication if P then Q, you've also proved the implication if not Q then not P, and vice versa. So just as I've got written here, proof by contrapositive can be useful when a direct proof is either a little bit difficult, or just sort of by flipping the statement around a little bit, it sort of gives you a different way to think about the problem. So again, we wanted to show if a and b are consecutive integers, the sum a plus b is odd. So think about that for a second. What would the contrapositive of that be? Well, okay, so this first if, that's our statement P. So if a and b are consecutive integers, then the sum a plus b is odd. So that's our statement Q. So now we flip them around and we negate. So our Q goes first, and we put a not in front of it. We're negating it. So if the sum of a plus b is not odd, then a and b are not consecutive integers. That's going to be our contrapositive, and that's what we're going to try to. We're going to try to prove this if-then statement. Okay, so this is going to be our contrapositive statement now. And I've got not underlined there once. Let's underline not in there again. Okay, so let's prove this. So we're going to assume that the sum of a plus b, so the sum a plus b is not odd. That's our assumption. So that means there does not exist, so there's our little exist statement, and we put a line through it. That means there does not exist an integer k. So there does not exist an integer k such that we can write a plus b as 2k plus 1. This integer k does not exist. Okay, so because if it did, right, a plus b would be odd. So this does not exist. So, well, we can again rewrite this. I could write 2k plus 1. I could write that as k plus 1. So this statement, a plus b equals k plus 1, does not hold for any integer k. But notice, since k plus 1 is the successor of k, this implies that a and b cannot be consecutive. Right? So since we can't write a plus b as some integer k plus 1, right? If we could do this, that would mean that those numbers are consecutive. But since we can't do that, so since this statement does not hold for any integer k, we've now shown that a plus b are not consecutive integers. So we've now proved the contrapositive statement, which again means, so we've shown not q implies not p, and therefore we've also shown p implies q, our original statement. So, okay, so I went through those a little fast because I didn't want this video to drag on too long. So 4 basic little proof techniques. Again, I'll make some more videos where I do each one of those techniques, and we'll look at some hopefully some slightly more complicated and more interesting variations, some more proofs. But again, this is kind of some basic proof techniques. There's some other, sort of tricky things you can do as well from time to time, but these are definitely the fundamentals. So if you're new to proving things, I hope this kind of puts you in the right direction. Again, and I shouldn't say here, it's not like this stuff is mechanical. There's still some subtle reasoning going on in all of these problems for sure. So if there's anything where it seems like maybe I went through it a little fast, definitely go back and look over it and take your time and really think about why those statements, what I said is true or correspondingly not true, depending on the situation.